equilibrium in chemical processes called chemical equilibrium is the most important characteristic of irreversible reactions. The characteristics of chemical equilibrium can be understood only when you are familiar with certain terms like reversible reactions and forward and backward reactions. So, let's get acquainted with these terms first. In general, the transformation of one substance into another is known as a chemical reaction. The chemical substances used at the initial stage during such transformation are called reactants, and the final chemical substances formed as a result of the chemical reaction are known as products. A reversible reaction may be defined as a chemical change in which the products can be converted back into the original reactants under suitable conditions. In a reversible reaction, the reaction in which the reactants react to give the products is called the forward reaction, while the reaction in which the products react back to give the reactants is called the backward reaction. Depending on the chemical nature of the products and the reaction conditions, the products formed may or may not react to give the initial substances. Let's take the example of the decomposition of calcium carbonate to demonstrate a reversible reaction. When calcium carbonate is heated strongly, it decomposes to form calcium oxide and carbon dioxide gas. When this decomposition is carried out in an open vessel, carbon dioxide, being a gas, escapes. Hence, there is no possibility for the products calcium oxide and carbon dioxide to react and give back the reactant calcium carbonate. Thus, the reaction proceeds in the forward direction only. Thus, the reactions whose products cannot be converted back into the reactants are known as irreversible reactions. When the same reaction of the decomposition of calcium carbonate is carried out in a closed vessel, the products, calcium oxide and carbon dioxide, combine to give solid calcium carbonate back. This clearly indicates that the reaction is capable of occurring in both the forward and the backward directions under favorable conditions. Such a reaction is called a reversible reaction. Reversible reactions are represented by a pair of half-headed arrows. If we plot a graph of a reversible reaction, we will notice that the rate of forward reaction is initially high. With the passage of time, the reactants deplete and the products accumulate. This leads to a decrease in the rate of the forward reaction and an increase in the rate of the backward reaction. After some time, a stage is reached when the rates of both the forward and the backward reactions becomes equal and the system reaches a state of equilibrium. We can graphically represent dynamic or chemical equilibrium as a forward reaction starting at a higher rate and a reverse process starting at zero rate coming together to reach an equilibrium point. Hence, when a reversible reaction is carried out in a closed vessel, a state is reached when the rate of the forward reaction becomes equal to the rate of the backward reaction. This stage is known as chemical equilibrium. It must be noted that the reaction can reach a state of equilibrium even if we start with the products, which is because equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be understood by studying a gas-phase chemical reaction. For example, when hydrogen and iodine are heated in a closed vessel, they react to form hydrogen iodide. When a mixture of equal initial concentrations of hydrogen and iodine are taken in a flask, maintained at 717 Kelvin, the intensity of the purple color decreases after some time. This is because, as the reaction proceeds, the concentrations of hydrogen and iodine decreases as they are consumed, and hence, the rate of forward reaction slows down. On the other hand, the concentration of hydrogen iodide increases with the progress of the reaction. As hydrogen iodide accumulates, the backward reaction of hydrogen iodide decomposing to hydrogen and iodine becomes significant. A stage is reached when the rates of the forward and backward reactions become equal, and the system is said to have attained equilibrium. At equilibrium, the concentrations of all the three species become constant. The graph depicts the variations of the concentrations of hydrogen, iodine, and hydrogen iodide as a function of time. You have already learned that in a reversible reaction, the reaction can reach a state of equilibrium even if we start with the products. Hence, the same state of equilibrium can be reached even if we start with hydrogen iodide alone. In this case, the concentration of hydrogen iodide will decrease and the concentrations of hydrogen and iodine will increase until they become constant at equilibrium. The attainment of equilibrium from either side can be shown in the form of a graph. The dynamic nature of the chemical equilibrium can be established by using radioactive iodine. When a small quantity of radioactive iodine is introduced into the above reaction in the state of equilibrium, it is found that the hydrogen iodide in the mixture contains radioactive iodine. This obviously shows that the reaction, though apparently standstill, is proceeding in both the directions. That is, the equilibrium is a dynamic equilibrium. Hence, the characteristics of chemical equilibrium are: equilibrium state can be approached from both the sides. The equilibrium is a dynamic equilibrium as both the forward and the backward reactions continue to take place with the same speed. At equilibrium state, properties such as pressure, concentration, density, or color remain unchanged over time. Equilibrium is possible only in a closed system. Consider the reversible reaction of nitrogen and hydrogen gases coming together to form ammonia. Is there any way to predict the extent of this reaction? Can we predict the direction of this reaction at any stage? Can we determine the equilibrium concentration from the initial concentrations for this reaction? These questions can be answered with the help of the equilibrium constant for that reaction. So, let's learn about equilibrium constant and its applications. In 1864, on the basis of experimental studies of many reversible reactions, two Norwegian chemists, Gullberg and Waag, established a relationship between the rate of chemical reaction and the concentration of the reactants and formulated the law of mass action. According to this law, at any instant, the rate of a chemical reaction at a given temperature is directly proportional to the active masses of the reactants at that instant. The term active masses in present times refers to molar concentration. In the early days of chemistry, concentration was called active mass. Hence, this law is known as the law of mass action. Let's see how it applies to the equilibrium state of a reversible reaction occurring in a homogeneous system at a given temperature. Let 1 mole of A react with 1 mole of B to produce 1 mole each of C and D. According to the law of mass action, the rate of forward reaction will be proportional to the molar concentration of the reactants A and B. That is, the rate of forward reaction RF is directly proportional to the concentration of the reactants A and B. Or RF is equal to Kf multiplied by the product of the concentrations of A and B, where Kf is the rate constant of forward reaction. Similarly, the rate of backward reaction will be proportional to the molar concentration of the products. That is, Rb is proportional to the product of the concentrations of the products C and D. Or Rb is equal to Kb multiplied by the product of the concentrations of C and D, where Kb is the rate constant of backward reaction. At equilibrium, the rate of forward reaction becomes equal to the rate of backward reaction. That is, Kf multiplied by the product of concentrations of reactants A and B is equal to Kb multiplied by the product of the concentrations of C and D. Or, this can be written as the product of the concentrations of products C and D divided by the product of the concentrations of reactants A and B is equal to Kf divided by Kb, which is equal to a constant Kc. Here, Kc is called the equilibrium constant of the reaction and is defined as the ratio of the product of the molar concentrations of the products to that of the reactants. The subscript C indicates that Kc is expressed in moles per liter. In the case that you just saw, the stoichiometric coefficients of the reactants and the products are unity. Now, let's consider a more general reaction of the type AA plus BB in equilibrium with CC plus DD, where A and B represent the stoichiometric coefficients of the reactants A and B, and C and D represent the stoichiometric coefficients of the products C and D, respectively. On applying the law of mass action, the rate of such a reaction is proportional to the concentration of each species raised to a power equal to the stoichiometric coefficient of the reaction. It, therefore, follows that at equilibrium, Kf multiplied by the product of the concentration of the reactants A raised to the power of A and B raised to the power of B is equal to Kb multiplied by the product of the concentration of the products, C raised to the power of C and D raised to the power of D. This can be written as Kf divided by Kb is equal to the product of the concentrations of the products C raised to the power of C and D raised to the power of D divided by the product of the concentrations of the reactants A raised to the power of A and B raised to the power of B. This is equal to equilibrium constant Kc. Hence, the product of the concentrations of the reaction products raised to their respective stoichiometric coefficients in the balanced chemical equation, divided by the product of the concentrations of the reactants raised to their respective stoichiometric coefficients, has a constant value at a given temperature. This is known as equilibrium law or the law of chemical equilibrium. The equilibrium constant for the backward reaction is the inverse of the equilibrium constant for the forward reaction. Let us prove this with an example. Consider the reversible reaction of hydrogen and iodine combining to form hydrogen iodide. The equilibrium constant for this reaction is written as Kc equal to the concentration of the product, hydrogen iodide, raised to the power of 2 divided by the product of the concentrations of the reactants, hydrogen and iodine. Let us say this is equal to X. Now, the equilibrium constant for the reverse reaction, hydrogen iodide disintegrating to form hydrogen and iodine, is written as K-C is equal to the product of the concentration of hydrogen and iodine divided by the concentration of hydrogen iodide raised to the power of 2. Now, this is nothing but the reciprocal of X, which is equal to 1 by Kc. Thus, the equilibrium constant for the backward reaction is the reverse of the equilibrium constant for the forward reaction Kc.